Okay, so first, I usually have an office hour from 11 to 12, but I have a meeting I have to be at today. So there's no office hour today. Is there anybody here who was, well, I talked to you, but anybody else who was hoping to talk to me at that office hour today? If are you available afternoon? Okay, can I meet you there around noon?
Yeah.
Okay, so I'll do that. Okay, and the second thing is you wanted to see number 20.
Yeah, we don't have to go through the entire thing. I just want to make sure that I'm
Yeah,
using the method correctly.
yeah. So this is particle kinematics. Oh my God, my computer is going crazy today.
Do Windows Shift S for the hotkey.
Windows
Windows
Shift
S.
S. You guys always, everything I know about computers is from you guys.
To be fair, there's way more of us than there are of you.
There's what?
There's more of us than there are of you.
That's true. That's true. Well, I know a lot about computers. Unfortunately, everything I know about computers is about the way computers used to be. So, like, I know more about writing batch files in Windows DOS than you guys do, for example. Okay, so this bike wheel, it gives us the diameter. It's moving, so when it says it's moving at a constant speed of 8 meters per second, that means that the center is moving at 8 meters per second. So I'm going to set it up like this. So the velocity of the center is 8 meters per second. And it's constant, which means that this omega is constant. Well, I guess we could do it sort of two different ways. Let's say, so I don't know why it says constant. If it's constant at the start and then it slows down to rest. So in order to stop, it's going to have an angular acceleration in that direction. And we know that the velocity of the center is equal to negative omega r 0, 0. And we can think of this as v. Well, this is going to be 8, 0, 0. And we know that the acceleration of the center is negative alpha r 0, 0. And we can use the constant acceleration equations from physics to calculate the acceleration AC. You could even start with it as, instead of going right to those equations that you learned in physics, you could start with a constant acceleration A and do the differential equations and derive those, but I wasn't expecting you to do that. And so let's see. In order to stop over a distance of 10 meters, what's the angular acceleration? So you can think of this as, I'm going to use this form of the equation. You might have seen it in a slightly different form, but it's going to be like 2 times the acceleration times the quantity P final minus P initial, or maybe you saw this as the change in position, something like that, change in X, is equal to V final squared minus V initial squared, something like that. Do you recognize something like that equation? And so we're saying it's going to stop in 10 meters. So we have 2 times A times 10 is equal to, the final velocity is 0. The starting velocity is 8. And so we have 20A is equal to negative 64. Bless you. And so A is equal to negative 3.2. And now we can say that this acceleration of the center is negative 3.200. Because it's slowing down, we know that has to be in the opposite direction as the speed, as the velocity. And now we have these 2 equations that we can use. I'm just going to use the X equations for each of these. So we have one that says 8 is equal to negative the radius of this circle. It gives us a diameter, so the radius is half of that. And so omega is 8 divided by 0.36. I don't have my bag. Can someone punch that in?
22.2.
22.2 radians per second, and this is negative. And then the second one says negative 3.2 is equal to negative 0.36 alpha. So alpha is just under 1. What's this? 8/9. So I think that's 0.89 about. Yeah. 8.8, right. Thank you.
You got it right.
Yeah, right.
What was the other method you said you could use for that?
The other method. Oh, the other way is, well, if you recognize, if you recognize that it has to be a constant angular acceleration, okay, if you recognize the connection between a constant translational acceleration and constant angular acceleration, then you could start with, like, you could say your angular acceleration as a function of time is, this constant. And then you could do the differential equation on that, and you'd come up with the same set of equations in angular form, which are like, you'd get one that said something like this. You'd get one that says something like this. All of these you recognize, they look they're the exact same form as the translational ones. And you'd get another one that said 2a times the change in the angle is equal to omega final squared minus omega initial squared. And then you could you could calculate that initial angular velocity this same way. You know that the final angular velocity is 0. You could calculate the change in theta and then, well, you could figure out the change in theta required for this thing to go through 10 meters and then calculate A that way. This should be alpha, not A.
That was what I tried first.
Okay. Okay, yeah. Yeah, I mean, it works the same way, but this uses stuff uses a direction you're more familiar with. Any other homework questions you want to see? Yes.
Are you gonna keep going with this problem or not?
Is it? Oh, I thought that was it.
The answer. Then how do you use the 10 meters?
Oh, to keep going with this direction? Okay.
In order to stop over a distance of 10 meters.
Okay, right. So you have to, so the circumference of this circle is 2 pi r. So can someone give me that as a decimal?
$11.83.
Okay, 11.8.
Oh wait, no, that's not right.
Okay.
Yeah, 2.26. My calculator was pulling wrong numbers.
Okay, 2.26 meters. So every 2 pi for a change in the angle gets you 2 pi meters. So so you can go 10 divided by 2.26 gives you, can you divide that one out? I'll do the first number, you give me the rest of the numbers. Okay, 424. And that's rotations, full revolutions. And so the change in angle is 2 pi times 4.424, and I multiplied and divided it 2 pi, so I could have made this a little simpler, but can you give me that decimal? .79 radians. Okay, so that's, and so now we'll take this and we'll say 2 alpha times 27.79 is equal to 0 squared minus 8 squared, and we get 55.58. Alpha is equal to negative 64.
Don't you have to use the angular velocities?
Yes. What is the angular velocity?
Negative 22.2.
Negative 22.2 squared. And that is a big number. And what do you get for that?
492.84.
492.84. And this change in angle was clockwise, so this has to be negative. So this is negative. So alpha is, okay, so something went wrong here, as you can imagine. So 0.7 times, this should be about double this, shouldn't it? Uh, no, 3 times, yeah, 3 times 0.7. So, okay, that's right. So in 10 meters, 4.42 revolutions. Oh, wait. No, that's right, isn't it? Well, divide that for me. Yeah, that should be about right. I was just thinking wrong. What?
Less than 10?
Yeah, right. Yeah. So let's say it's the same. Yay. Okay. Any other questions about that one? I know. I know. All right. Any other homework questions you want to see? All right. So now let's get back to, we started talking about particle kinetics. And remember that everything we're doing for now is in a non-rotating coordinate system. And in this class, anytime you use Newton's second law, or later when we get to rigid bodies, the moment equation, which I call rotational Newton's second law, that's moment equals I alpha. You need to draw a corresponding free body diagram. So I want to just list out sort of a set of rules for drawing free body diagrams. And I'll just always call those FBDs. So the first step is to draw a closed outline of the chosen body. So if you're doing a calculation about this guy, that closed outline would look like this. You don't have to be an artist or anything. But I'm trying to make an important point here. So this is a closed outline, okay? And there's no internal details of what's going on. There's no outside bodies. All we're trying to do with this free body diagram is make a clear distinction between what's inside our boundary and what's outside our boundary, okay? So this is the kind of outline you want. Here are 2 examples that you don't want. Okay, this one Why doesn't that one work? Because it's not a closed outline. There's no clear, there's nothing clear in this picture about what's inside and what's outside your boundary. The boundary is everything with these, okay? Also, what about this one? I'm already getting tired of drawing this guy. Yeah. This one is no good because you don't want to draw anything external to the object, okay? That ground, it's like, wait, are we including the top layer of the ground in our free body? Are we having to deal with the forces on that? We don't want any confusion about what's in and what's out, okay? So this should have no internal details. And no outside objects. Second, represent each not outside, represent each external load. And by loads, I mean forces and couples. We'll talk about couples in a while. Acting on the chosen object. Okay, so when I say, this is why it's so important to draw a clear boundary between what's in and what's out, okay? We only want to draw the loads on here that are being applied to the stuff in by the stuff out, okay? Now, when I introduced Newton's second law last time, what I said was the net force is equal to the mass times the acceleration, okay? So the net force is the sum of all the forces. This is kind of an important, interesting, almost like philosophical point about this. Like, think of how much harder our job would be in using Newton's second law if we had to represent every force acting on the chosen body, okay? Because that's really what it says, is like we have to, every single force acting on the body, we have to consider. And there's pretty significant forces acting, every time his heart beats. There are pretty significant forces pushing blood through vessels and stuff like that, okay? But we never have to put those in free body diagrams or in our calculations because those are internal loads. Do you have any idea why it is that internal loads don't need to be represented in Newton's second law? Yeah, that's right. So internal loads always occur as Newton's third law pairs, okay? So when his heart beats, his heart applies a large force to a bunch of blood, but that blood applies an equal and opposite force to the heart. And that happens at every single pair of forces happening inside that chosen body. The only place where you have forces acting on your chosen body and not the Newton's third law opposite force is at the boundary where you have something on the outside applying a force to the boundary, but the boundary is applying a force to something outside the boundary, and so we don't care about it, okay? So we've simplified the process of figuring out every force acting on the body to making it only the forces acting on the body by the outside, Okay, that's a really significant thing to be able to do. Okay. These external forces, I'm going to break them up into two types. The first is what I'll call field forces. The people who are taking physics 2 are pretty familiar with the idea of field forces, electrical fields, magnetic fields, things like that. People who watch Super Friends think field forces are a lot, when you grow up as a kid watching cartoons, you think field forces are a lot cooler than they are, like force fields or whatever. All a force field really means is you can imagine, it really just means that it's a conservative force. It means that if you know an object's location, you know the force that's applied to it, okay? And so one way you can imagine that field force acting is like there's all these kind of latent forces just hanging out in space waiting for the object to get to that location to activate it, So gravity is for us the most important field force. You can think like, okay, this thing has a certain mass, and right at this point, since the dawn of time, there's been this gravitational force waiting for this stapler to move through that space and activate it, and it's never done it until right now, and right now that field force is saying like, oh, I've been waiting to do my job, and now it's applying this force. That's what a field force is. That's what a force field is. So field forces include gravity. That's going to be, that's really all we're going to deal with in this class. But it also includes electric fields acting on charges, magnetic fields, any conservative force you could think of as a force field. Even spring forces you could think of as a force field, where you're waiting for this thing to be moved into location where the spring applies a certain force to it. And then the only other type besides field forces are locations where there's contact between the surroundings and the boundary of the chosen object. To represent forces in the free body diagram, let me keep saying loads so that couples are included too. If the direction of the load is known, draw an arrow in the direction of that load. And then label it with a scalar variable or value. scalar just means number. So you're not labeling this with a vector, you're labeling it with a number. Variable or value. If the direction of the load is unknown, draw arrows in the direction of the coordinate axes. And label it with a vector or a vector variable. Okay, so like for example, let's say that your chosen body is this car. People draw this two different ways. I do it like this. I draw like a little coordinate system here like this, and then my label would be like this. You also often see people do one in the direction of one axis, one in the direction of the other axis, and call it fx and fy, break it up into the components. Okay, but I'm going to do it like the one on the left. So now how do you know when you're done with your free body diagram? Just represent the weight force. Or, other field forces. I don't think I give you any problems where there's other field forces besides the weight. Represent each instance of the surroundings contacting the boundary. I'll say touching the boundary. And you're done. Yep.
How do you handle air pressure, wind?
Yeah, well, that just has to be, how you would represent it would be different in every case. We're not going to see any problems in this class where we do that, but you'd probably have to represent it as some kind of distributed load. It definitely would get more complicated, but that you'd still just think of it as, tiny little objects touching the boundary or a continuous object touching the boundary, Okay, so sorry, maybe for the people who took statics from me, maybe you've seen this exact picture before, I can't remember, but here's like an example. So let's say you're the unfortunate forensic physicist on staff when you're called to this scene, and there's like a truck, pickup truck. And this angry town person trying to push the pickup truck into this mud pit. And the truck is holding a helicopter. And the back of the truck is attached to a pig that's stuck in the mud. I mean, the pig, it's not like sad or anything. The pig likes mud. It's trying to get him out. And there's a giant bird standing on the pig. Like that bird in Up. Kevin? Okay, so there's a lot going on is the bottom line, right? And you have to do this calculation, and you're like, okay. But they say, okay, we want a free body diagram of the pig. Well, just remember that, so I don't know what a pig's legs look like. This looks like a cat. You can tell it's a pig because of the curly tail, though. Okay, that's the pig. I'm not redrawing it. So what does a free body diagram look like? Well, there's a weight force. And now that there's no other field forces. So now we're just going around the boundary looking for contact. There's contact at the pig's boundary from the mud. So I'll represent that, and let's say that's an unknown force, unknown direction force. I'll call that F mud. Okay. There's a force pushing down from, I'll say we know that the force from the bird is down, so I'll call that F bird. Yeah. And that, notice that this is a vector force that's applied to the pig from the mud. It's a scalar force because we know the direction. So this one would have components. This one would just be like 72, you know? And then keep going around the boundary and you get to the force being applied by the cable. That's going to be parallel to the cable away from the pig. And now we've made it all the way around the boundary. And so we know that free body diagram is complete. We have the field forces. We've represented every place of contact, and that's it. So the helicopter doesn't show up here. I mean, all of these things are affecting these, all these things going on are affecting the pig. I'm not saying they're not affecting it, but the way the helicopter, the truck, the man, the way those things affect the pig is just through these other forces. Okay? And so this is a complete free body diagram. And there's no reference to the helicopter or the man or anything. Are you with me on that? One thing we're going to use a lot is, so this is a notation we're going to use. For vector variables, And so be careful, we're not ever going to use this for scalar variables. We'll use a double subscript notation. The people in statics have seen this a ton. And so it's going to be like the force F with the subscript A, B. And the meaning of that is the force applied to body A by body B. So the first subscript in this class is always going to be the thing acted on, and the second one is going to be the thing applying the force. The benefit, and this benefit is going to come up over and over again, it's going to be really useful to us, is that Newton's third law, that's the equal and opposite reactions one, just says the force on A by B is negative force on B by A. So if you switch those subscripts, you take the negative. Okay. That's going to be really useful when we start getting into linkages, which are like the dynamics version of structures, just multiple bodies connected by joints. Okay, this is really important though. Don't ever use this for scalar variables because the Newton's third law thing doesn't work. Okay, and so if you write this double subscript notation and then you think you can apply it to Newton's third law half the time or whatever, it'll mess up your answers. Okay, so the next thing we're going to get into is three forces. Am I going to do three? Let's just do two forces. With known directions. And these are pushing contact and pulling contact. And with the pulling contact, we're going to think of this as as loads applied by cables and simple pulleys. And then I'm going to give you, I guess, really one category of force with unknown directions. So one is in the case of 2D problems, and we're going to do a lot of problems that are just confined to one plane. In 2D, this is a pin or a hinge joint. So like you can think of that as you know, something like this, connecting two bodies. And then in 3D, the version of that that we'll deal with is a ball and socket joint. And that's something like this that allows this body to rotate in any direction. So in 2D, this hinge joint applies a two-dimensional force like this, and we'll use the subscript notation for it. And in 3D, a ball and socket joint just has a third dimension on it, and you'd represent it the same way, except it has 3 components now instead of 2. Okay, any questions about any of that? So, oh, we don't have school on Monday, but on Wednesday, I'll get into these individual forces, and we'll start to be able to do some kinetics problems. Okay, that's all.